Probability and statistics are two sides of the same problem. Given an assumption about the state of the world, predict the outcome of a random experiment, and, given the outcome of a random experiment, infer the state of the world. Probability is easier since we're starting with a random variable x with a specific distribution. Statistics is much harder because we don't know the distribution of the random variable. However, since we're dealing with a random variable, we might be able to run the random experiment many times and recover a distribution. In a perfect world, we'd be able to get a perfect match between the observed outcomes and a known distribution. We don't live in that world. It would also mean that our experiment isn't random and that we're not actually dealing with a random variable. While we can't reliably infer the distribution, we might still be able to say something about it. Suppose x is a random variable with some distribution, discrete, continuous, whatever, and suppose we repeat the experiment n times and find the sample mean. Since the values of the xi are random variables, the mean is also a random variable, so we can talk about the distribution of the sample mean. Rather than find the distribution and compute its expected value and variance, let's find these first. We'll begin with the mean of the sample mean. So let's go ahead and compute that. First of all, the sample mean is going to be the sum of the random variables divided by n. By linearity, we can remove that factor of 1/n. That gives us the expected value of a sum, which is the sum of the expected value. But since our xi's are identically distributed, this just gives us n times the expected value of any one of them, which is just the expected value of x. And so the expected value of the sample mean is the expected value of the random variable. Next, we'll find the variance. By assumption, we'll make the trials independent. So the variance of the sample mean, well, that'll be the variance of the sum divided by n. And because this is the variance, we can remove that factor of n as an n squared, and then we have the variance of the sum, and our independence assumption tells us that this is the sum of the variances. But since these are identically distributed, that's just n times the variance of any one of them, and so it's 1/n the variance of any one of them. And so the variance of the sample mean is 1/n the variance of the random variable. So suppose x is a random variable with mean 10 and standard deviation 4. Find the mean and standard deviation of the sample mean of 100 trials of x. So our theorems tell us that the mean of the sample means, the expected value of the sample mean, that's the same as the expected value of x itself, which will be 10. And the variance of the sample mean, well, that's 1/n the variance of any one of them, and that's going to be and so our standard deviation is the square root of the variance, which will be Now, it might not be obvious why this is important, so let's consider the consequences. By Chebyshev's theorem, the probability a random variable is within k standard deviations of the mean is going to be. Now, suppose we wanted to find μx the mean of a random variable. If we run the experiment once, the probability we're within, say, 10 standard deviations of our mean is at least 99%. Now, in this case, our standard deviation is 4. So there's a good chance that our single outcome will be within 10 times 4, 40 units of the actual mean. Now suppose we run the experiment n equals 100 times and compute the sample mean. As before, the probability we're within k equals 10 standard deviation of the mean of the sample mean is at least 99%, but the standard deviation of the sample mean is 0.4. So there's a good chance that we'll be within 10 times 0.44 units of the mean of the sample mean, which is the same as the mean of the random variable. While the probabilities are the same in both cases, the interval is narrower within the sample mean. So the sample mean is more likely to be close to the actual mean. We can regard this as the fundamental theorem of statistics. The sample mean approximates the population mean. While we know the mean and standard deviation of the distribution of the sample mean, what's the actual distribution? With some effort, and that involves a few years of graduate school and some advanced mathematical techniques, we obtain the following result, known as the central limit theorem. Let x be a random variable with mean and standard deviation, and let x bar be the sample mean obtained when the experiment is repeated n times, assumed independent. Then the sample mean can be approximated by a normal distribution with mean and standard deviation, where the approximation improves as the number of trials goes to infinity. So again, if we go back to our example, but let's see if we can find the probability that the sample mean is within 1 unit of the actual mean. So we've already found the mean and standard deviation. To be within 1 unit of the actual mean, we need to be in the interval from 9 to 10, and we can compute our z-scores. And consulting our table, we find that our probability is, and that means it's very likely that our sample mean is going to be close to the actual mean.